one-dimensional wave functions and expectation values. So if we have a one-dimensional situation, then the wave function psi that we have defined to be a function of the coordinates of the system will actually only depend on x. So it will be only a function of x, and since the psi square, absolute square, is the probability density, the probability of finding the particle in an interval dx will be equal to probability density psi absolute squared multiplied with dx. And by psi absolute square, remember that we mean psi complex conjugate multiplied with psi, because the wave function can be complex. In an arbitrary interval between a and b, so instead of having an interval dx, an arbitrary interval a to b, the probability of finding the particle between a and b will be the integral from a to b probability density function psi square multiplied with dx. How does this work? Because in a small interval dx, the probability density function psi square can be considered to be a constant. It doesn't vary much in this interval. So from a to b, if we change these intervals and we integrate, if we add the contributions from all of these intervals dx from a to b, performing a Riemann sum, we would get the probability of finding it in the interval between a and b. This is basically counting for each interval dx, the probability, and saying that the probability of finding the particle between a and a plus dx, or a plus dx to a plus 2 dx, etc., all the way up to b minus dx to b. Okay, so now we have a special situation. The condition for the existence of the particle somewhere on the x-axis is called normalization condition. What is this? Well, if the particle exists, it has to be somewhere between minus infinity and plus infinity. So if we choose a and b to be minus infinity and plus infinity and integrate the probability density function dx, psi absolute square dx, we should get 1, because the probability of finding the particle between x equals minus infinity to x equals plus infinity should be equal to 1 if the particle exists. Now, this is basically shown with the annotation introduced by Dirac. That's basically showing these angular brackets. So if we have this angular bracket to start with, which is the less than sign, this is going to give us a bra. And if we have the greater than sign, then we have the ket. So bra, psi bra, and ket bra, when they come together, that is equivalent to saying we have the integral over all space absolute value of psi square integrated over all space. That's called the bra-ket notation. So going back to the probability of finding the particle in the interval between a and b, so here's our probability density function. So we choose a small interval dx. For example, if I consider this small interval dx between here and here, I will obtain, this interval is dx. You can see that I obtain almost no variation in the probability. So basically, I approximate this by taking the value at this point and saying that this value is the same in this interval. So that basically gives me the probability of finding it in this interval, and then I integrate over all such intervals. Okay. Now, what is the average position of the particle? The average position of the particle is called the expectation value of x, and it is defined by the integral over all possible x values, probability density function multiplied with x. But this is basically psi star, the complex conjugate x, psi dx. And using the bra-ket notation, because psi star is basically this one, and then we have x, and then we have the ket, psi ket, which is basically this one. So using bra-ket notation, if you see this, that implies we're looking at expectation value of the position. The expectation value of any function of x then would be the average value of f of x using these angular brackets. Using the bra-ket notation, this is basically psi bra f of x psi ket, which is the integral over all space complex conjugate of the wave function f of x, the wave function itself dx. So the function is multiplied with the probability density function and integrated over all possible values of x. This is basically the statistical definition of average value. So you take the variable, multiply it by its probability, and integrate over all possible values. That's exactly what we are doing here. Okay, so we talked about one-dimensional wave functions, the wave functions that only depend on x, and expectation values. So the probability of finding the particle in an interval x to x plus dx will be probability density function absolute value psi squared dx, which is psi complex conjugate multiplied with psi. In an arbitrary interval, it is the integral from a to b, probability density function dx, psi complex conjugate psi dx. And this is basically assuming that the probability density function, absolute value of psi square, does not vary much in this small interval dx. So we can look at the probability of finding the particle in this interval by multiplying it with its value at x, because x plus dx probability variation is very small. And then we integrate over all such values. This is basically performing a probability calculation for either or situation. So the probability of finding it here, either or here, either or here, either or here. So these values, all the probabilities add up. Basically, that's basically looking at the area under this curve. The condition for the existence of the particle is called normalization condition. The particle must be somewhere between minus infinity and plus infinity. So probability density function dx integrated over all space should give me 1. Using bra-ket notation, this is shown with angular brackets like this. The average position of the particle is the expectation value. Average value of x is the integral over all space psi bra x psi ket, which is psi complex conjugate x psi dx, and the expectation value of any function of x, average value of f of x is psi bra f of x psi ket, which is integral over all space complex conjugate psi f of x psi dx.